my drawer, and so where this $50 capacity and I'll be way more.
Yeah, may I print the cover page?
All right, I think we can get started. Today's our pleasure to have Shirley from SLAC. She graduated from Ohio State University, where she started working on neutrino physics, has been working on neutrino physics ever since. And today she's going to tell us about challenges in modern neutrino oscillation experiments.
Thank you. Hi. So we have a suite of neutrino oscillation experiments, both ongoing and in design stage. So today I want to talk about what are some of the challenges I think theorists face to make sure that these experiments have successful outcomes. And the background picture, you can tell, perfectly summarizes how I feel about the current situation. It's a giant pile of mess. There's so much confusion going on, both in the theoretical aspect and experimental aspect, and I mean, most often confusion on both sides are entangled together. So I am as excited about opportunities as the cat is about the urn. So hopefully at the end of my talk, you understand why. So I think next I have a very brief summary on neutrino oscillation. I think most people here are experts on it. So I will go through the first 5 slides very quickly. So 20 years ago, we discovered neutrino oscillation experimentally. The left figure shows that Super K measured the angular distribution of atmospheric muon neutrinos. And they see that compared to no oscillation scenario, there's a suppression in the outgoing direction. In the meantime, Snow measured the flavors of solar neutrinos. And with their very unique three-flavor detection channel method, they provide the definitive proof that of the 100% UE produced in the sun, 2/3 have oscillated into mu and tau. Now, I want to highlight the fact that as spectacular as these measurements are, these are rather crude measurements, because the effects we were going for are super large. For example, in the Super K scenario, there's an up-down asymmetry at the factor of 2 level. And similarly in Snow, the oscillation effect is as large as 60–70%. So these are not precision measurements by today's standards. Now, 20 years later, we've established this 3-flavor neutrino oscillation paradigm. We can compute all neutrino oscillation probabilities by 7 parameters. And we know that for the 3 angles at 1 delta CP phase are the parameters that determine the neutrino oscillation matrix, the PMNS matrix. And also for neutrino oscillation, we care about the mass square differences, because there's 3 mass eigenstates, there are 2 square differences, and okay. And of the 7 parameters, I would say that these 5 we've measured, and we're entering the precision era to measure these parameters. The accuracy we have now is only a few percent, which is very nice. And in fact, the current generation oscillation experiments are measuring more precisely the theta 2-3 and delta 3-2 squared. These 2 parameters, delta CP phase and mass hierarchy, are currently considered unknown, and these are the main parameters that we want to measure for the next generation neutrino experiments. Now, of course, luckily, or that you might have heard, that the ongoing experiment T2K and NOVA have started to have some very interesting hints about possible values for these 2. But still, at 5 sigma level, these 2 parameters are what the next generation experiments are going after for. Okay, so across the globe, there are several next generation experiments. So DUNE in the US, HEPEC in Japan, and Juno in China. They are all going after delta CP and mass hierarchy. Now, because I'm in the US, I'm funded by DOE. The rest of my talk will focus on DUNE. Okay, so what DUNE is, super naively. So DUNE uses a few GeV new beam accelerated in Fermilab. And these neutrinos propagate through 1,400 kilometers of Earth, reach South Dakota. And there, deep underground, there's a 40 kiloton of liquid argon detector that will measure how much of these new mu have turned into mu E. So that's a conceptual measurement that DUNE will carry out. Now, later on in my talk, I will talk about how the FAR detector measures neutrinos. And because this video is really cool, so I will show you how the FAR detector works at a conceptual level. Again, it's a 40 kiloton of liquid argon box. There's a drift field across the whole detector. And here neutrino comes in, and this will interact with argon, produce a muon and a proton. And muon and a proton would ionize in the liquid, leaving a track of drifted electrons. These electrons are drifted to the collection plane. So here, in the end, on the plane, you see the charged particle tracks produced from this neutrino interaction. So for now, you can remember this as it just measures tracks of charged particles above detection thresholds. Okay, so that was my short standard introduction for neutrino oscillation program, and hopefully you've heard it plenty of times. So sometimes I think what I just said would be wrongly summarized as that DUNE is a one-parameter measurement. It just measures delta CP. And I think that's the wrong attitude to approach this. So because these detectors just have amazing capabilities. So I think the first challenge for theorists is to come up with many compelling physics cases that DUNE can probe beyond the standard main objectives: CP violation, detecting the next galactic supernova neutrino, burst, and testing proton decay. There's so much more of physics opportunities out there that waits for us to be discovered. So next, I will quickly mention two of the physics cases that I've personally been working on. So the first one to me is super straightforward. Somehow, no one has looked at this before. So we know that we measure these parameters in neutrino oscillations, not only because we want to these parameters for their own sake, but rather what we're going after is to over-constrain the three-flavor neutrino oscillation paradigm. And hopefully that it's not entirely, it doesn't describe nature perfectly, and we can discover new physics. So on the left, I show one way how we're testing this in the quark sector, where hopefully you're all familiar with the figure on the left, that there are many, many measurements. Each measurement is represented with a long circle or some curve. And if the quark mixing matrix, CKM matrix, is indeed unitary, then we expect all curves to intersect at one point, which is the case in this figure. And we can carry out a similar test in the neutrino sector. And given the current neutrino oscillation data, the red figure is where we are. Now you'll see there's just a sharp difference in how well we are probing we are over-constraining the CKM unitarity and the PMNS unitarity. So one question is, after all next generation neutrino oscillation experiments, how well can we over-constrain the unitarity of neutrino mixing matrix? And that's something we're working on. And what we realized that in the neutrino sector, one way to illustrate how we are probing the unitarity is to plot on the angle plane. So in both figures, on the x-axis is sine squared theta 1, 3, and on the y-axis sine squared theta 2, 3. And the idea is kind of similar to before, in that each measurement will give you one curve. And if things are unitary, then we expect all the curves to intersect at one point. So the left figure shows the current measurements. So diabase reactor measurements provide a very precise measurement on theta 1, 3, and that's the vertical red line. And for the long baseline type of experiment, there's a disappearance channel, meaning you're measuring how much nu mu are still nu mu. And appearance channel, meaning you're measuring how much nu mu have turned into nu e.
So would this also depend on your hierarchy? Would this figure?
Yes, it does. Great question. So I think this.
I think it's
so for the
that for
current,
normal.
we use the T2K 2000. We use the last T2K analysis, which published separately disappearance and appearance channel. I think at that time they did not have sensitivity to mass hierarchy yet. And for the future, yes, it does. So this projection is done with assuming normal hierarchy. But things wouldn't look that different if you assume inverted. Great question. Right. So then for current experiments, we use the T2K analysis, and that the disappearance channel gives you the blue band, and the best fit is the solid line in the middle, and the shaded area shows the 1 sigma region. And the orange is the appearance channel. So you see that it's nice to see that right now, or at least using this data set, there's no discrepancy. All three curves intersect at one point. But unfortunately, the error bars are quite large, so the error is the shaded intersection. And this is something we can drastically improve with DUNE. So the right figure shows the projected sensitivity using DUNE. And you see both the blue and the orange shrink significantly. But diabase still provides the best measurement on theta 1,3. And one interesting measurement that DUNE is able to do that inspired us to do this is DUNE can measure a tau appearance. As we know, it's very, very difficult to measure tau appearance in neutrino because tau threshold is so high. Unfortunately, actually in this case, the tau measurement is not super precise. So the best fit would be this, the upper limit of the 1 sigma would be the green, and the error of the green band actually covers the whole area. That's why we did not plot it. So unfortunately, tau appearance is not as precise as the other channels. So this is work in progress. We're looking at, we can make similar figures with other oscillation parameters. But our goal is to plot this in the complex plane to make complex triangles. And we're able to do that with the delta CP measurements.
Sorry, I might have missed this. What canonical DUNE exposure, et cetera, do you assume?
Sorry?
What canonical DUNE exposure, et cetera, do you assume for these types of figures, like 40 kiloton?
So this is the CDR type of exposure.
Okay.
So like 300 kilowatt a year or something, which I think roughly corresponds to 7 years or so.
Okay.
Right.
So one more thing. So did you assume for delta CP, did you use the best fit value right now?
So these actually do not depend on delta CP so much because these are the real. So basically, unitarity has, it's either sum of the squares, so the real conditions,
So you
or the cross terms would be 0.
Cross term, okay.
Right. So these are squares.
Squares, okay.
Yeah. Any other questions? Okay. So another interesting measurement that we think DUNE can make is to measure solar neutrinos. So you can use solar neutrinos probe neutrino oscillation, as we've seen. That's the thing that was done in SNOW. And solar neutrino sector probe 2 of the oscillation parameters. That's the theta 1,3 and delta M2, theta 1,2 and delta M2 squared. And currently, the combined best fit from solar experiments on these two parameters is this colored region, and that's indicating 1, 2, 3 sigma, with the best fit kind of down here. But these two parameters you can also problem with the reactor experiments, and that's by chem length. So the results are in the black curves. And it's a little hard to see, but the best fit kind of disagree at about 2 sigma level. Now, 2 sigma may not sound super alarming, but I want to point out that when you look at this figure, really this is not measuring the same thing. These two measurements, although they're both oscillation measurements, really measure 2 different physics mechanisms. So the reactor measurements is neutrino oscillation in vacuum because of the setup, meaning that you're really probing the canonical first-year quantum mechanics oscillation system. So you are measuring the true oscillation parameters. The problem in the solar sector is solar neutrino oscillation mostly dominated by the so-called matter effect, meaning that oscillation is severely modified because solar neutrinos are produced in the solar core, where the matter density is extremely high. So rather than thinking this is an oscillation measurement, it's probably more appropriate to think of it as a measurement of cumulative neutrino interaction with matter as they propagate towards outside the cell. So this is an interaction measurement. So then this type of comparison, exactly what we expect discrepancies might show up if there are some, say, beyond standard model interactions between neutrinos and matter. So which makes this discrepancy more interesting. And another point about this discrepancy is this has been existing in dataset for many years. And if with the current generation experiments, the solar experiments dominated by Super K day-night effect, and Super K has been running for 20 years. So just a few years more statistics will not resolve this tension, and this is something that we just want to test. And we realized that DUNE can actually carry out amazing measurements for solar neutrinos. So again, left is present, and right is our projected sensitivity by DUNE and Juno. So if we think the current discrepancy is due to ESN interactions, then the 3 sigma measurement by DUNE will be this big, and that is 3 sigma projected sensitivity by Juno. So if this is indeed due to new physics, this can be discovered by next generation experiments with more than 5 sigma. And in addition, if you care about solar neutrinos, DUNE can also provide boron A flux measurements at 2.5%, improved from 4% measurement by SNO, and it can also make the first detection of HEPEC neutrinos. So DUNE is really an amazing detector with amazing capabilities. There's so much more physics case that it can probe, and we just need to come up with compelling cases. Okay, so now let's come back to the bread butter, what I call bread butter physics for DUNE, the CP measurement. So needless to say, measuring delta CP is not easy. It's a very subtle effect. And next, I'm going to focus on what are the theoretical challenges we need to overcome to make sure that we're actually measuring the correct value for delta CP. Okay, so conceptually, how does DUNE measure delta CP? So again, as I said, the measurement is basically a GeV nu mu oscillating into mu e. So both panels show the appearance probability as a function of neutrino energy. So you just need to focus, mostly you just need to focus on area region above 1 GeV. So the left figure shows the appearance probability for neutrino, and the right figure shows anti-neutrino. So for the left, if we look at the different colors, and given the different delta CP value, the bump roughly between 1 and 10 GeV would have different height. And that different height would tell you the value for delta CP. And for the anti-neutrino, if this is normal hierarchy, then all the probability in neutrino sector will be higher than anti-neutrino. And if this inverted hierarchy, all the probability in the neutrino sector, in the neutrino side will be smaller than the anti-neutrino side. So neutrino and anti-neutrino comparison gives you hierarchy, and the exact height in each channel gives you the delta CP, conceptually speaking. So basically what I want to say is DUNE measurement is a neutrino, you want to measure the number of neutrinos as a function of neutrino energy. Okay. So then how can we measure neutrino energy in a liquid argon detector? So here's a simulated event display, just kind of like the video I showed before. So the neutrino comes in at 0, 0, and that's indicated by the dashed line. And for this particular event, this neutrino produced a proton and a pion and a muon. And also these particles subsequently interact in liquid argon. And all these charged particle tracks will be drifted onto the collection plate. So every colored pixel would be some charge that you collect. So this is the neutrino event. And how would you reconstruct its energy? Well, the official method works as follows. So because it's neutrino charge current interaction, you always get a lepton. That's either a muon or electron. It's easy to identify. So that's, in this case, it's a muon. You first identify it, and then you find all the charge associated with this muon track. And from simulation mapping, that tells you what's the energy of this muon. Similarly, everything else that's not this charged lepton, you call it hadronic system. And you collect all the charge in the hadronic system and map it onto a hadronic energy. And you add it up, and that gives you the neutrino energy. So that sounds straightforward. Now, how would we characterize its performance? Well, the above method would work perfectly if the following things happen. So whatever energy, the neutrino energy goes into different channels, And if all of them would convert into ionization energy with the same linear rate, so that it's an exact linear mapping between the number of charges you collect and neutrino energy, this would work perfectly. That's more or less what happens with charged lepton. 1 GeV muon, if it gives you 10 charges, the 2 GeV muon would give you 20 charge. But the problem is that when neutrino energy goes into the hadronic system, there's a lot of missing energy channels. The energy doesn't come out as ionization. So then this missing energy varies on an event by event basis. So this is something that you would actually reconstruct. That this is a true neutrino energy, and this is the charge that you collect. So some event there's very little missing energy, but some event there's very large missing energy. And then the average will be smaller than a true neutrino energy. And you try to correct for this average. But if you do it wrong, then that introduces an error called energy scale. And even if you do it correctly, there's still a fluctuation of missing energy on an event by event basis, and that introduces energy resolution. So we want to correctly simulate what's the energy resolution, and we want to simulate what's the average energy loss so that there's no energy scale error. Make sense? Okay, so how would it simulate such an event? Well, obviously the first step is super important because that's a primary interaction, and this is simulated in the so-called neutrino event generators. Okay, so this is the area that has got a lot of hype in recent years, so neutrino-nucleus interaction cross-section. So relevant for DUNE, the energy scale involved is between 0.5 GeV to about 5 GeV. Now that may sound like a really small energy range, but unfortunately it's actually very large if you consider the physics degrees of freedom involved. At the very low end, if we're between 0.5 GeV to about 1 GeV, here it's in the regime of so-called quasi-elastic scattering, meaning that you can roughly consider the system to be a neutrino interacting with a nucleon in argon, where the nucleon can stay intact. So this is essentially a nuclear physics problem. When the energy goes higher, or energy transfer gets higher, this struck nucleon can become excited into baryonic resonances. So this is the region of so-called resonance production. And of course, when the energy transfer gets even higher, essentially you're interacting with the Planck degrees of freedom in the nucleus, or in the nucleon. And this is the so-called deep inelastic scattering regime. I do want to point out, for people who are more familiar with DS, in that we're never going above 5 GeV. So if you're familiar in the DS in the collider setting, this energy scale is much, much lower than what's happening in collider. So in recent years, people start to say that should not really be called DS, because whenever we say DS, people get the impression that, oh, that's a well-established framework, we know how to compute stuff there. But it's actually not. So in neutrino experiments, we're barely here, so people say that we should call it shallow elastic scattering. But in any case, even if you don't compute these processes, it should be easy to see that you're exactly sitting in the transition region between nuclear degrees of freedom versus particle degrees of freedom. And transitioning between EFT is always difficult. So, and on top of that, everything here happens in the nucleus environment. So other than computing the primary cross-section, you still have to put it in argon, which is a difficult problem on its own.
So one question. So for 500 MeV, those nucleons you were treating as free nucleons, or really you were doing nuclear physics?
Great question. So that's what I meant by you have to put it in argon. So they're definitely not free. So, but are not that subject to nuclear models. Okay. In that, for example, the most naive treatment for this is to put it as in nucleus using a Fermi gas model. Okay. And that kind of works, like not really well, but reasonably okay. So not at a level that you will consider a shell model. No other questions?
Actually, a question about your previous figure. Is that like, if you go back to your histogram, actually before that. Is that like a detector? Is the width of that set by the detector or set by just a phase-based thing? So what sets that?
A great question. That's
Okay.
like one
Okay,
of
you're
our
running. Okay, if you answer that, that's
results.
fine. Go ahead. Okay.
But if your question is not answered at the end.
I will
ask.
answer. Yeah.
Okay. So computing the primary vertex is complicated. So then what are some of the questions I personally would like to see answered in the field? So first is, what is our current theoretical understanding? How well can we compute this? Which surprisingly is not known. And also, how much will this nuclear cross-section or cross-section uncertainties impact delta CP measurement? Will this introduce a CP error of 10 degrees, 20 degrees? Will this possibly bias CP measurement of 10 degrees? We don't know. And assuming that the current theoretical errors is larger than what's needed, then how small do we need to get? Should we get a cross-section, should we aim to compute cross-section at 1% level, 10% level? How to quantify that? And lastly, if we know that we should aim for a cross-section calculation of 1%, how will we get there? So that is the list of questions I'd like to see answered. And next, I will show my work regarding the first question. First, I just like to emphasize that I just said, okay, there are roughly 3 kinematic regions that contribute to the cross-section. And it really matters that it's 3 regions because clearly they are using very different they have to be computed using very different theoretical framework. And their treatment are rather separate in the community. So the first question is, what is more important? Is it mostly quasi-elliptic scattering on nucleons, or is it mostly DLS on quarks? So that's illustrated in this figure, where I use the kinematic variables of Q squared as the formal lensing transfer squared, and Buran X on the y-axis. And this color map shows the event distribution in DUNE detector with the standard flux and stuff. So the darker region shows there's more events. So the quasi-elastic interaction on nucleons are here. And resonance production is this line, and actually it kind of overlaid with PS, so there's resonance production here as well. And the darkest region is deep inostic scattering. So, which means that most of the events in DUNE are these almost interacting with quarks. Now, this actually matters a lot because depends on your exposure for this cross-section issue. I think the nuclear aspect of the problem has gotten a lot of attention. People fully understand that modeling of argon nucleus and putting nucleons in them is difficult, and the nuclear response to neutrinos is also difficult. But that is mostly impacting the quasi-elastic part, which contribute to a lot of events, but it's not dominant contribution. The dominant contribution are really from these things that are currently computed using DS formalism, but does not work very well. Okay, so how can we assess the current theoretical uncertainties? Well, it's not straightforward because these cross-sections are computed event generators, like Gini or Gibu. And these event generators don't provide you with theoretical errors. So one way, of course, to guess an error bar would be to cross-compare with event generators. But a slightly better thing we can do is to compare them to data. And there's extensive precise electron nucleus cross-section data that can be used to validate these models. And the reason is, so the diagrams I draw before is neutrino interacting with the argon-40. Now this diagram is almost exactly the same if you replace that neutrino vertex with neutrino line with the electron line, because the hadronic treatment are exactly the same, and that's the difficult part. And these generators treat the hadronic part the same, whether it's neutrino scattering or electron scattering. So here I show data compared to generator prediction. These are 4 GeV electron beam, and they are scattered off at a 16-degree scattering angle. And this is only inclusive measurement. So the data with the error bar should be compared to the black curve. And also the colored line indicating which channel, according to the generator, contributes to the total cross-section. So here we see big problems. First is, well, the agreement is really not great. This is at 20, 30%, up to 50% level. Next thing is that the quasi-elastic region, as I said before, really works reasonably fine at this precision. But the thing that really does not match is the resonance production and DS. I mean, there's just no agreement between what's happening in Gini DS and People DS. So, any questions about this?
So resonance is not working. That's a kind of interesting thing. I thought that you already know all the resonances. It should have worked better, no?
Yes.
So is that the nuclear physics the issue here?
It's not really clear. I guess these are mostly probed in JLab type of experiments, so it's probably closer to should be called with nuclear physics. But the difficulty is that I don't think we have data that excite nucleus and have the branching ratio. There's by the way, there's many resonance states. So there's delta, that's the first one, but in generators they include like 30 or so resonances. So then, I don't think there's data that record how much, say for argon, you excite to each resonance with 30 different branching ratios. So that's not available. And
because the difference is huge. Because resonance is that is the cause. Because
yes,
quasi-elastic is coming down fine, but resonance is not picking up.
right. Yeah, I think that's one of the interesting results that we see. Both resonance and DS, and there's another issue of what you call resonance and DS in these event generators. So resonance treatment DS are obviously completely different. So then there's a question of how do you basically connect these two, because they obviously have overlapping phase space, and that's also not clear how to do that. Right. Okay, so disagreement's really not agreement's really not good, but this is at a particular kinematic. This is 4 GeV at 16 degrees. There's a lot more electron data we can compare to, and this is sort of like a global overview. Again, this is Q square on the axis and Y on the y-axis. And the error bar, the color bar indicate the percentage difference between data and generators. So if we roughly see for people, there's a couple regions that kind of saturate the arrow, my color scale, but mostly are under it, which means that across the whole phase space, Gibu and data kind of agree at 20% level. Maybe a little bit worse than, but not much more. Whereas Gini, it completely saturates the color scale, so you can't read what's the disagreement. But we look at it, and it's roughly at 70–80% level across the entire kinematic region. So it's really not good. And if you're not familiar with these two generators, Gini is actually the most commonly used generator. It's in fact used by all formula-based neutrino experiments. And then lastly, I want to point out that, so we plotted all available data for electron scattering. Now, one thing that you might remember is for DUNE, the most relevant, the region where the highest event density is kind of here, where the data is actually cut off. So in the most relevant kinematic region, there's actually very little data coverage, even at the inclusive level. And there's like a couple data sets at exclusive level. So data coverage is also rather poor. Okay, so again, we said that's just the inclusive level. But of course, when you simulate events, you also need to simulate the outgoing particles. So how does generator do when it compares to exclusive data? So here's a neutrino comparison. So Minerva is an experiment that measures neutrino nuclear interaction. And here I'm just showing that what they measured are pion distributions compared to Gini prediction. So here they only use Gini. And you just ignore all the other colors, just see the data with the black points compared to the black line. You see that things really, really disagree, not just the overall factor, but also the shape. Both in the pion kinetic distribution and pion angle, the features are just off. So current generators really do have large uncertainties that they don't explicitly quantify. So the statement is probably that we're looking at uncertainties level of, somewhere around 50% at inclusive level, and at explicit level it's even larger. Okay, so the next question is how much does this uncertainty actually impact the value of delta CP for measurements? And now we have to come back to what I said about energy reconstruction. So just to recap, that for experimental measurements, the errors we care about is energy scale bias. So if you simulate wrong how much missing energy you have on average, and energy resolution, which is the fluctuation of missing energy on an event-by-event basis. Okay, so then an obvious question is, what is the missing energy channel for a neutrino event in DUNE? Okay, so this is a little bit confusing, and I just want to explain this clearly. So if you want to compare the missing energy, one thing you can do, for example, is to take one generator, say simulate event with Gini, and then compare it to the prediction by Ibu, or reconstruct it with a different event generator. And then you will get an energy bias error, and they would predict different energy resolution. So you cross-compare two event generators. That seems like the most straightforward way to test this. So, but before you do that, you can do a simple test. So sanity check, that you simulate event with Gini, and you reconstruct it with Gini. So this should give you 0 energy scale error, because you should predict your missing energy perfectly. And this should give you 1 energy resolution number, and that should be consistent from whoever does this analysis. So that is what we did as a sanity check. So just to illustrate, if we use 1 event generator, both to simulate and to reconstruct, we should expect only 1 energy resolution and no energy scale error. Okay, so is that the case? Obviously no, because otherwise I wouldn't be talking about this. So as I said, the most commonly used event generator is Gini, so that's what we used. So it was the default Gini configuration before last year, so everyone else used it. And there's quite a few groups in the field that have studied this. So everyone's using the same Gini default cross-section models, and everyone trying to get an energy resolution out of it. Presumably use reasonable set of energy reconstruction procedure. So this shows the disperse of the results. So energy resolution should depend on neutrino energy, and that's okay. But the results vary by, for this one, the energy resolution is as large as like 20%, and as small as 5%. I was using the same event generator. So when we saw this, we were completely surprised, because we were hoping to skip this step and just use previous results, but there was no consistency between other results. So then we decided to study what actually happens, assuming that you have no cross-section problem, what happens with energy reconstruction. Okay, so just to get a better sense of what is the system. So a neutrino coming, you always get a charged lepton. So charged lepton can be reconstructed really, really, really well, so we'll mostly just ignore it and only focus on what's happening with the hadronic system. So I keep calling it hadronic system, but what is it? Well, it turns out that it's roughly an equal partition between protons, charged pions, neutral pions, and neutrons. And each carry about almost 10% of the neutrino energy. And But on an event-by-event basis, the composition of the hadronic system can really, really vary. For example, here I show just the first 10 4 GeV neutrino interactions that I simulated. And the numbers on top is the energy goes into the hadronic system. So the rest goes to the charge lepton. And the color shows the composition. So this is just to illustrate that things really vary on an event-by-event basis. For example, for this one, you have out of 4 GeV neutrino energy, there's a 2 GeV basically pi-0 shower. So that comes out as gamma. And in this case, this is a big shower. This is a 3 GeV hadronic system that is almost entirely pions. And then some events, for example, this only has 30 MeV energy, and that's just a tiny proton, very soft proton. So things really vary. And also, for example, in this case, there's neutrons here. So at this level, we can already kind of guess what will be missing energy. Because I said, conceptually, DUNE just detect charged particles above threshold. So then the first obvious missing energy channel is some of these particles might be super, super soft. So for example, this is a 30 MeV proton. That might be below threshold. And another obvious missing energy channel would be neutrons, because neutrons are not charged. You might worry about gammas, but for all practical considerations, gammas and electrons are the same, so they're actually quite visible. So neutral particle, neutron, and some soft protons that fall below threshold. So if we consider that, then this is probably the conclusion we'll get. For after primary vertex, this is the energy budget of the hadronic system. So the whole pie is the entire hadronic system. And of that, 80% with what I label as ionization, so that's visible. And you lose 20% of hadronic energy to neutrons. And only 2% to particle below threshold. So this procedure takes the event generator and cut on the outgoing particles with neutrons and thresholds, are a very common procedure that a lot of these phenomenological studies of cross-section uncertainties take. This is rather intuitive. The problem with this approach is that it's rather misleading. Because as we saw from the event simulation, yes, there's a primary event, but there's a primary interaction. But there's a lot of subsequent re-interactions that they introduce large amount of missing energy. And you cannot just discard them. So if instead after this primary vertex, we also propagate the subsequent particles in local argon, then this new pie chart is the missing energy channel. So now there's a lot more stuff, and you don't have to read them all. I'll just point out a couple. First is threshold. So in the previous slide, there's only 2% energy goes to sub-threshold particle. So then if you draw a conclusion from that, who cares about threshold? But after we repropagate particles, there's a lot more energy fall below threshold. So that's this 20% here. So then you have to think seriously, what are the thresholds of the detector? And I'll come back to that the next slide. And another slice I want to talk about is this nuclear label. So that's nuclear breakup, meaning that if a neutrino come in, interact with argon, if they inject 3 protons or 2 neutrons, a bunch of other things, you are left with a nucleus that's smaller than argon. Say silicon. There's binding energy difference between argon and silicon. And that's from a particle detection point of view, that's a missing energy. Now you might think, well, we're dealing with GeV of neutrinos. Nuclear binding energy is a 10 MeV scale process. So who cares? Well, it turns out that because there could be many, many subsequent re-interactions, this nuclear breakup energy could account for 17% of the missing energy. So it's actually rather important. But this is an energy budget that people just didn't consider before because it might seem small. Okay, so what are the detector thresholds? So again, don't have to read this slide. This is one of the super confusing things that we find. Basically, the numbers in the literature vary by orders of magnitude, plural. So for example, the left table shows the CDR, so the particle detection thresholds from CDR, so the official DUNE document. And the numbers are, like tens of MeV to 100 MeV, which sounds rather large because it's a TPC detector. So 100 MeV pile should be quite visible. But that's the number in the document. And then on the other extreme case, there's a small-scale argon experiment in Fermilab that's been taking data. That's called ARCU. And in, I guess, last year, they have demonstrated that they can pick up charges as low as sub 1 MeV. So they're able to see electrons that's at 0.5 MeV. So that's what they consider to be threshold. So the threshold in the literature changed between 100 MeV to 1 MeV. And that would obviously impact how much missing energy go into subthreshold particles, which would affect, if one generator tend to predict harder particles, one generator tend to predict softer particles, that would really affect this.
So how about photon threshold? Like, is it also like a sub MeV?
Photon threshold?
Yeah.
Great question. So I think it's also very low. Not as low as electrons because a 0.5 MeV photon probably would pick out the electron that's even smaller. But in the similar ballpark, like also 1 or a couple MeV.
Yeah, because there will be lots of excited states of the nuclei, and that would handle very much.
Exactly. Actually, that photon is what they would measure in this analysis. They are measuring the de-excitation gammas. And I certainly remember they have been as low as 1 MeV. I'm not sure like what's happening below that, but it's very low. Okay, so this is just to illustrate that in order to properly take into account the theoretical uncertainties, it matters what experimental input you use. And because this is such early stage for DUNE planning, the numbers from the experimental input just changed by quite a lot, and you have to make your best guesses in terms of what is most reasonable. Okay, and one particle that seemed to draw some attention is neutrons, because obviously they could be a potential channel for missing energy. And there's also a lot of confusion on exactly how visible are neutrons. So this is something we look at. Roughly speaking, in these neutrino interactions, the neutrons produced are on the order of, their spectrums show on the left, so a couple hundred MeV neutrons. And here I'm just trying to show that neutrons show up very differently, one from the other. So for example, here I injected a simulated 500 MeV neutron at 0, 0. And all the dots, I'm not sure how visible they are, all the dots are energy deposition. So it's hard to see that's supposed to be. There's just not much you can collect. And these dots come from neutrons bouncing in argon. Excite argon, there's a de-excitation gamma. And they just bounce around, which is why it's just little blips. Whereas for the next event, luckily there's a hard interaction here, and they pick up a proton track. So this is a 20 centimeter track that should be quite visible in a detector. So for this particular event, you should be able to pick up quite a bit of neutron energy. And the next one is somewhere in the middle. And again, these three are also the first 3 random events that I picked out. So the point about neutrons is, I think it's just simply too early to say how well we can detect neutrons. If we can catch every single blip somehow, then actually up to 50% of neutron energy could be visible, and that's not lost. But if your reconstruction algorithm is not super smart, it's also possible that we may lose most of neutron energy. So I think that's just very hard to say at this point. Okay, so there's a lot of room in terms of what you assume can be detected, but let's make a set of what we consider reasonable assumptions and see that, again, given one event generator that is 100% correct, what is the energy resolution that you get? And we consider 3 cases. The first one, we just use CDR threshold. We think that's a little bit too conservative, but that's the official number. And then we're getting threshold that's about, we're getting energy resolution that's about 20%-ish. The next one is an improved improvement from the current official procedure, where we think you don't have to just collect charges of hadronic system and map it to one number. But because we know the charges could be from protons to pions, which have different quenching factor, if you don't know what that is, ignore that. But it's something that, in principle, you can correct for. If you do that, then we can get energy resolution of about 15%. And this one uses very, very low thresholds. And if we use, sorry, I get it wrong. So if we only lower thresholds and not correct for this quenching factor, we can improve the energy resolution to 15%. If we correct for that, the most optimistic scenario, very optimistic, we think energy resolution can be as good as 5%. And back to Lee's question. So for the best reconstruction scenario, because we got rid of everything that can be corrected for, the energy resolution is set by nuclear binding energy. Basically, how often neutrons are exciting argon. And that's a 5% effect. And this difference, and in addition to that, almost 10% is due to this quenching effect. So protons, because protons are slow, protons are ionizing slower, so they are less efficient at producing charge compared to pion. So how much proton and other stuff you have. And this additional 5% is due to, and a little more, is due to very high threshold if you use CDR numbers. Okay, so this just to say that there's a lot more uncertainty you can introduce if you're not using super, super low thresholds and not using smart reconstruction methods to try to get rid of, to correct for effects, all experimental effects that you know are there. Okay, so assuming you can do that, then the uncertainty is nuclear binding energy. So again, most nuclear binding energy is from neutron interaction, so what really matters is how much neutron you're producing out of your event generator. Okay, and so because neutron propagation is important, that's introducing the nuclear binding energy. Of course, that is also something we like to simulate correctly. So these are simulations of subsequent reinteractions. That's also done in simulation packages. And this is a recent measurement that we see where neutron interaction in argon are measured compared to two most popular propagation codes that study neutron interaction in argon. And this is essentially similar to neutrino-nucleus event generators, where you can see the data are up here and the simulations are down here. So every step of the reinteraction is simulated in packages, and there's large uncertainties. Similarly, these generators don't give you error bars, so it's hard to say like how consistent these are. But it is also important to certainly measure them and update these cross-section libraries. But it's a good direction to see that there's measurements of neutron interactions in argon and in oil. Okay, so now back to we decided to study this because we want to do a sanity check, and in the end we finally understand that why different groups are getting different results, because they're using different experimental inputs, and we figure out what we think is reasonable set of assumptions. So now we can see that if we use different event generators and use the best reconstruction method, then what is the energy scale error that we're getting? And this is a preliminary result. The energy scale error between two generators, I think this is simulated with Gini reconstruction feature, are these two lines, the best reconstruction method. Look at this blue line. And it's a function of energy, but it's roughly, say, at 6% level. And in comparison, the DUNE CDR goal for energy scale error it has to be smaller than 2%. So this is one way to show that current generators are definitely introducing a much larger uncertainty than what we are aiming for. Okay.
Do you remember what is captain again? Where is it? What is it? And where is it There's a
Captain is, or mini captain, is the experiment that was run in Los Alamos, where they used the Los Alamos neutron beam.
So
Okay, yeah,
captain
sorry.
means,
That's good, yeah.
that's the captain means.
That's the, okay, right, okay, never mind, I got it now, sorry.
Yes.
Brain cramp.
Yeah, because of this,
Yeah.
because how important neutron propagation are.
Yeah,
It's
exactly.
super actually important that captain can do their calibration measurements. Okay. No more questions on this? Okay. Last, how can we, okay, so what level of accuracy is needed? That's a very difficult question. That's a work in progress. I have nothing to show there. But how can we reduce the current generator uncertainties? Well, certainly many experimental effort in many directions and theoretical efforts are needed. And I'll just flash one proposal that we're working on right now. So in SLAC, we have this proposed experiment called LDMX, Light Dark Matter Experiment. Its main science goal is to measure, is to probe dark photon models. But experimental setup is like follows. There's a 4 GeV electron beam that will hit a target, thin target, and it can be any kind of solid. And then we can measure the outgoing electrons in this ecal and different hadronic particles. And for dark matter searches, the idea is we want none of these hadronic particles. So if there's anything in the hadronic calorimetry, which is discard event, looking for a very energetic electron beam. And if the electron would brainstorm a light dark matter, then there's a strong missing energy search. So we're searching for no hadronic system, only electron, but then there's still large missing energy. That's the dark matter search mode. But looking at this, we realize that, aha, this is the perfect design for a cross-section measurement. Well, because you have electron beam of a few GeV, we can use any kind of target we want. And there's good forward coverage and great tracking capability for all hadronic particles, and obviously the outgoing electron as well. So here's just a figure to show how much phase space that it can cover because of the beam of the energy and the size of the tracker. So again, here's the phase space distribution of DUNE, but it looks different from before because we decided to switch units between two papers. So here the x-axis is the energy transfer. So incoming electron energy minus outgoing electron energy. And on the y-axis is still the form momentum transfer. And again, DUNE near detector event density is this color map. So the DRS region, DS residence production region, is this block right here. And you just need to see that this blue line indicates where we can probe it with the highest, most scattered electron angle, that's 40 degrees. So LDMX can measure essentially everything below 40 degrees, so everything below this line. So it has really a great access of the most important kinematic region for DUNE. And unlike the previous electron scattering measurement I showed you before, those are only inclusive measurements. So here, not only can we measure the electron, but also our outgoing hadronic system of particles. So we're very excited about this proposal. Hopefully it gets funded. Okay, that brings me to my conclusion. I personally think next generation experiments are extremely exciting. There's so much physics potential that's not being probed yet. And these measurements are hard, definitely difficult. So the cross-section is one aspect of the uncertainty that's most interesting to me. And there's certainly so much theoretical and experimental effort that's needed to make sure that we can actually measure the value that we say we're going to measure. So, thank you.
Thank you, Shirley. Any questions?
So for the electron beam dump, what did you do? So you were looking at this electron. Okay.
So are you I same question. Are you turning you want to turn DUNE near detector, or you want to turn LDMX into DUNE near detector?
Well,